Hey guys, so it's Richard, and as requested, I'm doing some videos on center of mass stuff. So this isn't a real screencast, but I set this up so I can actually write, which is going to go a lot faster, and it involves 2 giant boxes of Cheerios, don't ask. So pretty much what I wanted to do first was to go back through the derivation of the center of mass formula for n objects, because you can think of it as an average, but it was really helpful for me to sort of get a better idea of where it came from. So obviously, if we're trying to find the center of mass of a ruler with some weights hanging on it, we're going to be trying to figure out the center of mass. And so, if you think about a seesaw, the force exerted by a weight on it is directly proportional to its distance from the fulcrum, or in this case, what we're thinking of as the center of mass. So, if this block A, is twice as far as block B is from the center, then block A is going to exert twice as much force down as block B is. So if block B weighs twice as much as block A, then the forces are going to balance. So additionally, if we allow the distance that something has from the fulcrum or the center of mass to have a sign, we can say that block A is negative 2 units away from the center, and block B is positive x units from the center. And so what that allows us to do is actually say that if you take the relative downward forces of all of the blocks, they're going to add up to 0. So you end up with something which looks like this, which basically means that for each block we're going to take c minus the position of the block, which is the distance from the center of mass, and obviously weight it by the mass. And if you add all of those up, you're going to get 0. So, for instance, in this case, if you add up negative 2x times x plus 2a times x, you're going to end up with 0, because the system balances, and this is the center of mass. So what this means for us is we can do some expansions. So the summation of the position of the center of mass times the nth mass minus the position of the nth mass times the mass of the nth weight equals 0. The summation of all the masses times the position of the center is equal to the summation of all of the positions times all of the masses. And so this is getting something that starts to look like our original formula. So you end up with C equals the summation of all the positions times all of the masses over the summation of the masses. And as you can see, in the case of 2 masses, you end up with this same formula. The position at the center equals the first mass times the first position plus the second mass times the second position, all over the total mass of the system. Yeah, so that's all good for a finite number of masses, and so the sort of tricky transition here comes when we try to generalize to I guess an infinite number of masses. So the way that this happens is you do pretty much, well, first of all, it's always going to be over the overall mass of the system. So if we're adding up a bunch of infinitesimals, the center still equals something divided by the total mass. Or if we want to think of it as the continuation of this formula, it's going to be something divided by the integral from 0 to the thickness of actually, this is just going to get confusing, so scratch all of that. So we're going to think of this instead of, I was jumping ahead and getting to things of uneven shape, but we're going to do this for a ruler of non-uniform density. And we're going to say that the density of our little ruler here, some distance I from the end is going to be f of I. So the denominator of the continuation of this is going to be something divided by the total mass. So it's going to be the integral from 0 to x, which is the total length of the ruler, of f of I di. So you're adding up all of the infinitesimal masses of the little slice of ruler. That's just a normal integral. It's nothing too exciting. For the top, for the numerator, what we're doing is we're just extending this. Once again, it's going to be going from 0 to x, so it's going to be the integral from 0 to x. And you're going to be adding up, instead of a finite number of weights like you have here, it's going to be a bunch of weights, so a bunch of infinitesimal weights. But like this, the position of one of these little infinitesimal guys is going to be I. So it's going to be I, which is the position, times the mass of the ith slice, which is going to be f of I di. So we end up with the sort of integral analog of this finite summation formula. And if you replace the f of I with lambda, the linear mass density, then you get pretty much what we learned in class. So this is where this formula comes from. Then what I like about thinking of the math, or the density at a point as a function, is that you can just as easily say we have a triangle here, this is going to be I, and the thickness at this point is going to be f of I instead of the density. So yeah, and that'll help us later on. So anyhow, this is how you arrive at that formula, which is very helpful later on. And I guess it's equally true to have what Mr. Siegel said about the integral of mass with respect to x, or the integral of x with respect to mass, whatever it was, all over mass. But personally, for me, this just helps more. So the next video, I'm going to do the semicircle center of mass problem and actually apply some of this stuff. So yeah, thanks for listening.